In this video, we're going to talk about nuclear magnetic resonance, NMR, and how does it work, and go through a couple of exam-style questions that you'll need to know. But the important thing is that nuclear magnetic resonance is basically analysis only for exams. Okay, so we look at the analysis of it, but first of all, we need to understand the process. So I'm going to get you in this video to understand the process. So let's look at a molecule. So this is ethanoic acid, as you can see, our normal model of ethanoic acid here. Now the process you need to understand to start off with is that every nuclei, every nucleus, and all the electrons around it. So you can see the electron clouds around the atoms here. We can see just the atoms here. All of it has different magnetic fields. So the electrons have a magnetic field, the nuclei have a magnetic field. And depending on the size of the nuclei, depending on the numbers of electrons and so forth, which all atoms have different numbers of electrons, protons essentially, that means you'll get a different magnetic field around each one. Now, you can use that magnetic field to find out what environment the nuclei are in. I'm going to explain to you why that works. So in the next few slides, we're going to use some simple visual models and animation to try and help you understand how this works. We're going to represent the nuclei of an atom just as this rhombus, because it helps you see that it spins. And you can see the spinning that happens now. That spinning that happens has to be what's known as a half spin. So for example, half, 1.5, 2.5, for example, for it to be seen in nuclear magnetic resonance. Now that's not CEST, it's not particularly important, but what it means is that half spin is dependent on the fact you have an odd number of nucleons, which is protons and neutrons. And the two which you're going to do in your exams is carbon-13 and hydrogen. If you think very quickly, carbon has 13 nucleons, hydrogen has 1, both odd numbers, which means they'll get this half spin that we're talking about. So let's have a look at, for example, 3 nuclei. Remember they're spinning, okay? And then put them in a very, very strong magnet. So this is your really strong magnet. Now they can be in line with the magnet, okay? Or they can be opposed to the magnet. So think of them throughout this animation that they're aligned if they're pointing upwards, and then if they're opposed, they're pointing to the side. And we'll show you that in a second. Now, they can move in 3 different axes, okay? And in real life, they waggle as well, but we're not going to go into huge detail. We just want to get you to understand. So here we have in line with the magnetic field, and then we put in some energy, and it's opposed. Now the energy we put in is a radio wave in NMR. And you can see this radio wave coming in, being absorbed by the nuclei. The nuclei becomes opposed. Then the final one, okay, we can see that the radio waves in the nuclear magnetic, on the NMR, get absorbed, and then when it returns, it gives that energy back out again. You'll see here it turns and it gives energy back out again. Now that energy is then detected by a detector, and you can see that you get a signal. Now if you have 2 different nuclei in 2 different environments, they'll give 2 different signals when they return back to being in line with the magnetic field. And as you can see here, there are 2 different environments. Those 2 different environments can be then converted using some very complex mathematics, okay, and they can be converted into something we can interpret. And so if the nuclei are in different environments, we can see. Now the x-axis on the NMR spectrum, which you will see, is indicating the frequency, but it's converted into something called chemical shift. And the chemical shift tells you which can be used to tell you what environment each one of the nuclei is that you have detected. So for example, if I've got 2 different nuclei, the purple one and the red one, so red one, purple one, you will see 2 different signals, as you can see here on my NMR spectrum. Now there are 2 different types of NMR that you're going to come across, and as I said, they will give you information about the nuclei of the atoms, okay, and tell you which nuclei they are, for example, if they're hydrogen nuclei or carbon nuclei, and they'll tell you the environment in which they're in. There are many videos on NMR, and the way in which this section of the course is organised is the fact that you will do this, which is how does NMR work, then move on to carbon-13 NMR, and then move on to the exam style questions in carbon-13 NMR, then we'll do proton NMR, and then there are many, many examples of proton NMR that you can work yourself through. So let's carry on with this video. So data obtained is the number of nuclei and the environment the nuclei are in. So we'll go through in exam style questions how you are to present that. The next stage though is really important. You're going to have to know what solvents are used, and this is an exam question. So deuterated solvents are used as deuterium gives no peak. So you can see the green areas is exactly how you're meant to answer the question. You have to say that deuterium gives no peak. Now, the most common one is a deuterated chloroform. And again, we're only saying this for proton NMR, hydrogen NMR only. Now, the deuterated chloroform has deuterium instead of hydrogen, and the deuterium has an even number of nucleons. It has 2, okay, so it's not seen by the NMR. The next one is a reference. So we need a reference in NMR that everything comes off. So basically a reference is set to 0 and everything comes off that. And the reference we use is tetramethyl silane. Now tetramethyl silane is well away from other peaks and is one sharp peak. So this is tetramethyl silane. And you can see that there's 4 carbons around the outside and 12 hydrogens. So basically there's a lot of carbons, a lot of hydrogen. So if we're doing carbon NMR, there's a strong carbon peak. Okay, if we're doing hydrogen NMR, there is a strong hydrogen peak. Okay, now it's well away from everything else, like we said, and so we set it to 0 and everything comes from that. So let's, for example, take our NMR that we produced earlier in the video with the red and the purple nuclei. We've got a chemical shift this time, okay, and there's our 2 peaks. And then this orange peak is our tetramethyl silane. So you will not see it in the NMR because it's taken out by the machine itself, but that will be set to 0 and everything else is relative to that. And it is an examinable question here, is what is used as a reference in NMR, and it is tetramethyl silane to give that chemical shift to 0, well away from other peaks and a sharp peak.